Hello, my name is Asaf, and I want to tell you about this joint work that I have with Yvonne Verburn on what we call the grand arc graph. The main point is that we construct this graph, which is infinite diameter and delta hyperbolic, and the mapping class group of an infinite type surface acts on it by isometries. But this action is also really nice because it acts continuously on the boundary. So first, I want to tell you a little bit about infinite type surfaces, just like the one on my shirt, actually. So an infinite type surface is a surface that has either infinitely many punctures or infinite genus. This one has both. This one, the cycloctopus, just has infinitely many punctures. And we study these surfaces by looking at their end space. And the ends, loosely speaking, is the ways in which you can go off to infinity. So in the top surface and in the bottom, you can either go off to infinity on the to the left, or there's like a Cantor set's worth of directions where you can go off to infinity on the right. So mapping class groups are exactly the same as for finite type surfaces. They're the groups of homeomorphisms up to homotopy. And just like in the finite type case, there's this idea that we might be able to study their mapping class groups by their actions on combinatorial objects, like the curve complex. Well, maybe not like the curve complex, because for infinite type surfaces, the curve complex has diameter 2. And here's why. See, I have an infinite type surface, and if I have any two curves in it, it doesn't matter how wound up they are, I can always kind of like sneak off to infinity and find another curve that's going to be disjoint from both of them. Uh-oh, that's bad. So this has been remedied a little bit in the past. So there's some work by Bavard and Bavard-Walker, and some work by Fanoni, Gazwala, McClay, highly recommended, really, really fun papers that deal with specific examples of surfaces, and they construct a subcomplex of the arc graph, which is delta hyperbolic and infinite diameter, and the mapping class group acts on it by isometries. But what about other surfaces? So this is where the work with Yvonne and I comes in. And to do this, we have to talk about this partial ordering on the end space. So the Mann-Rafi ordering, it says as follows. It says if E is an and F is an and, then E is less than F if any neighborhood of F contains a copy of any neighborhood of E. So maybe let's do like a quick example. So I have the flute surface here, which is just a puncture at every whole number, and there's two ends that are kind of like going off to infinity. And in this case, it's exactly what you think it is. The ends that are punctures are less than the ends at plus or minus infinity, and the ends at plus or minus infinity are equivalent to each other. There's a nice theorem that Mann and Rafi prove about their ordering, which is that this ordering has maximal ends, if you believe the axiom of choice. And these equivalence classes of these maximal ends are either Cantor sets or finite. And here's like the key idea of the work that I do with Yvonne, which is that these maximal ends are kind of like, if we think of arcs between them, these arcs are kind of like you can't kind of go off to infinity and avoid them. You can't sort of push them away. They're kind of always there. And so we define a grand arc to be, or we define an arc to be grand if its endpoints lie in distinct self-similar equivalence classes of maximal ends. What does this mean? Well, I have my equivalence classes of maximal ends. Some of them are Cantor sets. So like type 1 here is a Cantor set. And then I have some finite ones. And I'm allowing arcs between the finite ones, but not from the infinite one to itself. And I'm also, of course, allowing arcs between different equivalence classes. So here is, so the grand arc graph is the subgraph of the arc graph consisting of grand arcs, of course. And here's like an example. So it's kind of a modified cycloctopus. I have 3 arcs here. 2 of them are sad because they're not grand. This one is not a grand arc because it goes from a maximal end, the one with a bunch of genus on it, to an end that's not maximal. But the other one is sad because it goes from between 2 maximal ends in the same equivalence class. But the green one is happy. It goes between 2 maximal ends of different equivalence classes. Cool. So what do we actually prove? Well, we show that if the surface has at least three self-similar equivalence classes of maximal ends, then the grand arc graph is, okay, it's infinite diameter. That's really good. It means it's not trivial. It's delta hyperbolic, which means that it has a boundary and we can do like a bunch of happy geometry on it. Plus, the mapping class acts by isometries on it. And this mapping class action extends to a continuous action on the boundary, continuous in both the mapping class and in the grand arc graph, because the mapping class has some weird topology on it. Moreover, if the surface is stable, which is some technical condition that I don't want to get into, then the mapping class group acts with finitely many orbits. So why do you care? Like, what can we do with this? Well, if you can study the boundary of the grand arc graph as some space of laminations, just like Bavard-Walker and Bavard do, then you can create interesting mapping classes, like mapping classes that really mix up the entire surface, not just a finite part of it. And finally, you can also like think about maybe a classification of mapping classes on infinite type surfaces by looking at their orbits on the boundary. Maybe I can talk more about that some other time. So thanks for listening, and I hope you guys have a really good conference. Bye-bye.